So, first of all, I would like to tell you that I have uploaded lecture 5, like yesterday's lecture. Lecture 5 means handouts of lecture 5. And I also have uploaded assignment 2 and hint solutions of assignment 2. And another announcement is about your exam date, which hopefully I'll be uploading all your exam schedule. But for the timing, let me tell you that your first test hopefully will be conducted on test 1 is on February 2nd, which is a Tuesday. So during the class time, which will be 12 noon to 1 p.m. And this exam will be actually of 45 minutes. So you'll be given 45 minutes of time during this 12 to 1 p.m. depending on whenever you log in to the system. And test 2 hopefully will be on February 23rd. This is also a Tuesday, so it is also from 12 noon to 1 p.m. So here also it will be of 45 minutes. And here the topics for the second class test 2. It is on random variables and spatial distributions, which I will be discussing in this maybe next 2 weeks. And here on the first test, the topic is whatever we discussed before the random variable. So I could say axiomatic theory of probability or axiomatic definition of probability, including everything. Okay. So so whatever we discussed before defining random variables. Okay, we started talking about random variables yesterday or not. So random variables. Yeah. And I'll upload the schedule when it is final about all the tests. So hopefully there will be, it seems now, 4 tests. 2 in February, 1 in March, 1 in April. And of course the test. Okay, this test will be fill in the blanks type.
Sir,
Mm-hmm.
sir, in the last test, there will be full syllabus, or in the only the syllabus after the test 3?
You are asking about test 3?
No, sir, I am asking about the syllabus. Sir, in the syllabus is there, or section wise, or the full syllabus in the last class test?
Syllabus I already topics means the syllabus. I already announced syllabus for the topics for first test and second test. What is your question?
Sir, I am asking
Sir,
about the last test.
Last test means which one?
Like, sir,
the very
Second
last.
one.
Okay, that I will discuss later, no? So this is
So
test 1 and this is test 2. Is a
Sir,
topic for test and tester.
sir,
Yes.
sir, when did you upload assignment number 1?
You have to go and check. I
Sir,
think I have.
actually,
Let
Sir,
me
do we
check.
actually,
sir do we have to submit
I don't
assignment?
remember. No, no, no. I did not discuss that, right?
Sir,
So
what is the
assignment
platform of the test?
1 I uploaded 19 hours ago. So maybe yesterday I uploaded. You can check, okay? Because the date
sir,
is also given there.
do I have to
Microsoft
submit
Teams.
these assignments?
If it is, then I will announce, right? I didn't announce, means you don't have to.
So what is the platform for these tests?
That will announce later.
Okay, and they'll be of fill in the blank types.
Yeah, I have written here.
Okay, okay. Thank you, sir. Thank you. Thank you.
Mhm. Any other question? Any other question related to the exam? Yeah, the other test like test 3, 4, 5, whatever it is, we'll be announcing that. Okay. Yeah, so exam today, don't worry about exams. Okay. I mean, don't worry means you do not worry about the process of the exam. The syllabus and this is how it will be conducted, and every other administrative details will be communicated to you, I think. Okay. By me or by the coordinator of the course, Professor Samas Kumar. Yeah. Okay. Any more question? No. Okay, so let us continue our discussion. Mm, so we started talking about random variables yesterday. So we started talking about random variables, and we said a random variable is nothing but a function from the sample space to R. Whatever you want to define, you can define that. And we have discussed one or two examples. For example, we talked about the rolling of two dice. One is, let's say, dice 1. This is die 1. This is die 2. So these are the outcome of die 1 and die 2. So the possible outcomes are like 1, 2, 3, and so on. 6. Here also 1, 2, 2, 6 here. So basically, I can say that this for this particular experiment, these are all the possible outcomes. So I can say the sample space. So here we know the sample space explicitly. So the sample space corresponding to the experiment or the example of rolling a pair of die. Pair of die is what? Pair of dice is what? Is S, let's say, which is all such pairs X, Y, let's say, where 1 is less equal to X, less than equal to 6, X and Y both. I mean, 1 less equal to X, 1 less equal to Y less equal to 6. Yeah. So this is my sample space. And then what we said is we just defined a random variable yesterday, that X. Okay, X of any S, which means here X of any XY, which is equal to, let's say, X plus Y. This is what we have defined for all S is an S. So all the sample points, this is what we define. Now see, if we assume here that that all possible outcomes are equally likely. So that means how many sample points are here? Mod of S is the number of sample points, which is equal to 36. So then probability of xy, if they are all equally likely, happening of any xy where xy belongs to S, or I can just write mm, S here, just S, okay, is equal to 1 by 36. Okay, and this is true for all x, for all S is in S. This is what it is. What was the motivation to introduce random variable? We said, okay, first motivation is to associate real numbers with possible outcomes, because for example here it is a pair of real numbers or pair of numbers, let's say, where this x, y, x is from 1 to 6 and y is also from 1 to 6. So instead of writing, you see that probability of all explicitly 1, 2, 1, 1, 3, 3, everything, we just said probability of S, okay, where this is a sample space. This is equal to 1 by 36. And what we defined is, we defined a random variable x, capital X. This is my random variable, which is x plus y. Now the question is, if we want to understand the importance of this, yeah.
Are you writing something?
Yeah.
Sir,
You cannot
seems the
see it,
screen has frozen. The screen has frozen, sir.
but I can see it in my desktop. Okay.
Yes, sir.
Let me.
It is.
It is visible or not?
Yes,
Sir,
sir.
it
Yes,
is
sir.
visible, but it is stuck.
Okay, just a minute. Let me. Can you see it now?
Yes, sir.
Okay. So yeah.
No,
So
sir.
what you can't see it?
No, sir.
You still cannot see it. I mean, because it is visible.
So we
Sir,
can see.
it's visible, sir.
So it is
Yeah,
visible,
it is
sir.
yeah. If you cannot see some of you, then that was maybe it is a problem in your machine. Yeah. So x equal to, let's say, yeah, this is what we define association. But then the question is, okay, we have associated numbers with the sample points. Okay. But the question is, how do I use it? Okay. So how do I use it means how do I use it to solve problems? Solve problem means calculating or finding probabilities of events. So my first job will be to define events through this association. That means through this random variable. And I said, how can we explain these events? I gave you an example. For example, I said, okay, if I write just x equal to a, so it means this is the set of all events. I mean, instead of writing this, I can say this equal means this is how it is defined. Okay, whenever I write three parallel lines, so or line segments, it means it is defined as the set of all outcomes, possible outcomes, as such that x of s is equal to a. This is how I define it. If I define it, this is less equal to a, it means this is set of all outcomes, possible outcomes, such that x of a is less equal to a. Say this is a here is a let, can write like let a belongs to R. A is a real number. Then x of s, this is a real number. So it makes sense to write x is equal to a, all is equal to a. Similarly, I can write it is bigger equal to a. That also has a similar meaning. So s belongs to s. such that xs is bigger or equal to a. I can also write, let's say, a less equal to x less equal to b. If I write like this, so here that means b is also a real number. Then what I mean by this symbol is that this is the event. So that means the set of all possible outcomes such that for which the values are lying between this a to b. Now see here, for example, in this particular example, I mean example of the roll of pair of dice. Okay, if we said if a equal to, let's say a equal to 2 and let's say b equal to 5, then if this, then I can say then a less equal to, that means a less equal to x less equal to b, which means 2 less equal to x less equal to 5. So this means set of all outcomes. So what are those outcomes? We can say it is 1 1, I can say it is 1 2, and so on. You can say 2 1, you can say 1 3, 1 4, and what 2 3, 2 2. Okay, so 2 3, 3 1, 4 1. Okay, 3 2, and so on. I think this is what it is. So this is set. That means why is this is the event? This is set, and now here I must write it that this is a subset of S, and any subset of the sample space is an event. So this explains an event, as these are all subsets of S. So now I can say that okay, these are all even. For example, this is an event which is just given by this condition. Then the question will be here: how do I calculate probability of these events? Like if I want to ask what is this, what is this? Okay, so this is important. Okay, so it is not only an association, but we want to use this association to calculate probabilities of different events. Now, as we said, there can be two kinds of sample spaces. As we discussed, sample spaces can be of two types. One is discrete and another one is continuous. So this is discrete, let's say, and this is continuous. So the random variables corresponding to the discrete sample space is called discrete random variable, and for the continuous sample space, it is called continuous random variable. So here, whenever we are talking about this particular example, that tossing of the coin, then here, I mean, rolling the pair of dice, here we are actually talking about a discrete sample space. This is, so we are talking about a discrete. Is it stopped, the broadcasting presentation? Can you see the?
So we
No,
can
sir.
see.
Yes, sir, we can
Yes,
see
sir,
it.
we can see.
We can see.
There is some message it is showing to me.
Sir, we can
Due to
see, sir.
you can see?
We can see. Yes, sir.
Okay, just a minute. Okay, so now the thing is, can you see? Because I cannot see it in my desktop. That's why I'm asking.
Yes, sir, we could
Sir,
see.
we can see it.
Oh, okay. So, yeah. So this is yeah. So now, so this particular example is a case of discrete random variable, and in discrete random variable, our main focus will be on what we call the distribution function or the probability mass function. Okay, so I'll define what it is. So probability, I'll tell you why it is important. Probability mass function, or what is called the distribution function. Distribution
So I guess you are
function.
writing, but it is not getting displayed on our screen.
Yes, sir.
Yes, sir, like the screen is frozen, sir.
Yes, sir. We only see the till the continuous part.
Okay, just a minute. Okay, again sharing the screen. I think now it should work. Give me a minute. Yeah, can you share it now?
Yes, sir. Now it's visible.
Yes, sir.
Okay, okay. So now for the discrete random variable, okay, we'll define what is called the probability mass function. And what is that? I think this also I discussed last day for a moment, which is like probability. So which is like probability of x equal to x for any x, small x. So for any small x in R. So if I know, so this is what, this is the probability of this set, this particular event, set of all sample space such that x of s is equal to small x. So if for any x, I know this probability, I can write it as a function of x. Because depending on the x, I'm getting a value, which is the probability of the corresponding event. And this function is called the PMF, probability mass function, or the distribution function. So this is called sometimes PMF, probability mass function, or the distribution function. Okay, and if I know this, then I know, okay, probability of all the events which can be described this by this expression that capital is equal to small x. So if I somehow get to know about this function corresponding to this random variable capital X, then I know probabilities of all possible events corresponding to capital X equal to small x. That means I know many things about the probabilities of the events, because many events possibly can be written as capital X equal to small x. Okay, if it is not, then the question will be, if there is an event which cannot be expressed as this capital equal to small x, then the question that will be different question. The question will be, how can we use this information to calculate probability of an arbitrary event, let's say. Okay, and if somehow this is known or this is given, let's say, okay, then we know many things about the probabilities of the events, and if we want to find probability of a new event, then we have to use this information. Okay, so for example, if I ask you now, what is the probability mass function of this event, this random variable of this example? So here on the previous example, the rolling of a pair of dice. So here is the question. So what is the probability of the random variable in previous example, in the previous example of rolling a pair of dice. Now see, if I want to, if you just look at it, then you will see how it is defined. So let me draw a table. Okay, so let's say this is x. Okay, and these are the probability of x equal to x. Now we can actually find out this thing from, because this, if all possible outcomes are equally likely, we can find it out. We'll see how we can find it out. So what are the possible A's here? Possible A's for which this will be non-empty. So this is, if you want to construct this table, first we have to find out what are those x? What are those x? Small x. So first look for those x for which x equal to x is a non-empty event, or I'll say a non-trivial event. Non-trivial means it is not a null set. Okay, non-trivial. Trivial events are what? Null set and the entire sample space. So trivial, non-trivial event. Now what are those? Because you see, how did we define the random variable? It is just the sum of the this is just the sum of this x plus y. That means what happened in the first die and what happened the number which is shown in the second die. If we just add them up, this is how it is defined. The random variable is defined. So the possible values of the random variable could be starting from 2, and then it could be 3, it could be 4, and so on. So if I just, and it could be up to, let's say here, 6 plus 6, 12. So now, so if I just write it down, then you'll see that x could be 2. This is one possible value for which the corresponding event, capital X equal to small x, is non-empty. So if we have x equal to 2, then what is the corresponding event? What is the corresponding event? What is x equal to 2? What is the corresponding event?
1,
Just one.
One.
So what is, okay, so what is its probability? Probability, see, here all the outcomes are
1 by
equally likely.
36.
Yeah, so it is 1 by 36. Similarly, if we write x equal to, let's say 3 is a possibility, okay? And then this event could be 1, 2, and 2, 1. Then what is, so if I write x equal to 3, the probability will be 2 by 36. Because all outcomes are equally likely. If we write x equal to 4, then this will be 1, 3, 3, 1, and 2, 2. So if we write it as 4, then it will be 3 by 6. And if I keep on doing this, so I'll get up to 12. Okay, so if I keep on doing this, and if I write x equal to 12, then the event will be 6, 6, the event. So here the probability will be 1 by 6, 1 by 36. Now the question is, can I define a function fx here such that for all x, okay, whatever the value I give, so from 2 to 12, let's say, for all x, whenever I put x equal to something, some number, this will be given to me. That this number will be given to me. Can I define a function x? Okay, I mean, you need to speculate, you need some time to find that, but I will give you the answer, let's say. You'll see that this could be a function, okay, x minus 7 by let's say 36, okay. If you put x equal to 2, then you see it is 1 by 36 and so on. Then you see that this is a probability mass function corresponding to the the random variable which is described for, or which is defined for what is rolling of 2 dice example. Okay, so this is an example. In what happens is, in a practical situation, you will not be asked to define a random variable and find out what the function is. But in most of the cases, when you get a real data, okay, real data means data can come from anywhere. It could come from a physical experiment, from physics lab. It can come from some data analysis related to some economics, data related to economics, data related to anything actually. Okay, then you'll you'll have an idea about the sample points, and then you have to make a guess about this fx. And if you know this fx, then gradually you will develop the theory. Then you'll see that many things about the data will be known from this function fx. So it will not be supplied to you sometimes, and sometimes for some standard examples, like I said, in class test 2, I mean the test 2, the syllabus is about spatial distribution. And what do I mean by this here? Spatial distribution, you will see. Spatial distribution means I will consider some examples of random variable where this will be given to you. this function, this probability mass functions, okay, will be given to you, and using that, then the question will be, what can we say about that random variable, okay, for which the probability mass function, okay, follows a particular kind of an expression. For example, we'll talk about binomial distribution or binomial probability mass function. So for that, then the question will be, can I find out what are other properties, or what are other things, other stuff, okay, which we can say related to the corresponding random variable. Okay, so there are two things here now. One is, in a practical situation, this you have to estimate this this probability mass function corresponding to a random variable, which you probably define, which means something. For example, here in this particular example, if the capital X measures the sum of the outcomes, okay, possible outcomes of the pair of dice. Then for your data, it could be something else which will measure something, and then corresponding to that, you want to find out all this particular function, small fx, which will give you probability of capital X equal to small x. Okay, so let me consider another example. Okay, let me consider another example, which is, let's say I toss a coin. Okay, tossing of a coin. I am just giving you some examples because to get a feeling about what is a random variable, how does it work. Okay, so tossing of, let's say, of a coin, but I want to toss the coin, let's say four times. Okay, 4 times. This is what I do, and let us also assume that coin is unbiased. Okay, that means head and tail, they are equally likely. I mean, if you probability of getting head in a toss is half, and probability of getting tail is also half. Okay, this is a balanced coin, so this is an unbiased coin. Okay, so if you do this, then what are your, I want to now define, let's say, a random variable here. Okay, what is my sample space here? My sample space, okay, if I just directly go and draw this the table, so that means my sample space would look like this. My sample space will look like, okay, so okay, so let us say that my sample space will be what? If I draw it 4 times, it is like H, okay, or pair of this thing, or you can just say something like this. I can just say something like this: X, Y, Z, W, such that X, Y, Z, W belongs to H and T. Okay, this is my sample space. So now I want to define a random variable from here to R, let's say, and my interest is at the number of heads. Okay, number of heads in a coin, in a toss of a coin 4 times. Okay, so that means what are my possibilities? What are the possible values of x, and what are probabilities of x equal to x? Let's say I want to find it out. Okay, so one thing to say, how it is defined, this x. So I can say, okay, if x equal to, I mean, if the sample space equal to h, what is happening? So h, then, okay, so if the sample space is like h, okay, this is my sample space. That means this is my, let's say, s equal to this. This is my samples. This is my sample point. Then I have a corresponding probability. Okay, the probability will be like, what will be the probability here? Well, this is a balanced coin. So 4
1 by
times.
16.
So that means, yeah, 1 by 16. Yeah, 1 by 16. Okay, so what is the value of x here? X is here equal to 4, let's say. Okay, so I'm giving this table in a different way, and then we'll see, I mean, how to construct this. So, and then I can also see T, and then here I have the power 1 by 16, and here 3, and so on. So what are the possible values of x? X could be equal to such that capital X equal to small x is a non-trivial event. It could be 4, 3, 2, 1, 0. Okay, it will be like this. So now if I want to fill up this table, what are the probabilities of the corresponding this thing? Okay, then I can fill it up. Okay, And can anybody tell me what will be the corresponding? Okay, so let me fill it up a little bit. So x equal to 0, it means what is the corresponding event? TT. So what is the probability of that event? It is 1 by 16. Okay, because the corresponding event contains only one possible outcome. Okay, if I take x equal to 1, so that means one hit can appear. So how many such outcomes could be there? So it could be head HTTT. Yeah. So how many such? 4 by 6. Yeah, 4 by 16. Then I can have x equal to 2. If I take x equal to 2, how many? So what is the probability of the corresponding event x equal to 2? Capital X equal to 2.
6 by
6
16.
by 16. Okay.
Can you
Okay.
once more
What?
explain how you are computing P of x is equal to x?
What?
Can you explain once more how you are computing P of x is equal to x in the right
Yeah.
column?
P. Okay. So x equal to x, which is the event. Okay, which is defined as this way. So all such sample points such that capital X of x is equal to small x. Okay. So now if we say x equal to, let's say, 0, it means in this particular example, the set of sample points, okay, for which the value of x, this x is here equal, let's say, x of s, let me define it as the number of heads, okay, in the outcome s. Okay, so capital X equal to 0, this one, it means what are the set of outcomes for which number of heads is equal to 0, and there can be only one such possible outcome, which is this. Now I want to calculate the probability of this. I said that all the coins, the coin is balanced, so it is unbiased, and there are 16 possible outcomes. So this will occur with probability 1 by 16. So that's why I get 1 by 16 here. If I just write capital X equal to, let's say, 1, so it means number of heads. What are the possible outcomes for which the number of heads is equal to 1? So in that case, my sample space will be, let's say, H, T, 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 or it could be T, H, let's say, T, T, or it could be T, T, H, T,
So, sir,
or it could be,
you are defining x, the random variable x of s is equal to number of heads in s, and then you are
yes,
computing
yes,
the corresponding probabilities depending on the number of heads appearing in each event. I
yes,
mean,
yes,
each
yes,
experiment.
yes, yes, yes. Okay, so if I take the values of small x could be 100 also. You can take small x could be 100 also, but small x could be right 100. There is no event. I mean, there is no outcome for which 100 number, because you're only tossing the coin 4 times. So the number of heads could maximum take the value 4. So if you write small x equal to 100, so then that will be a null event. Okay, the null set. So the probability is always 0. So here I'm in the table, in this table, I'm just writing down the probabilities of the events for which you have a non-zero value. Okay. So yeah, so you can write 3 and then you can write 4 and so on. So for example, okay, let me just complete this x equal to 1. So and then what can happen? Okay, so T, 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 and then H. So then you see that probability of capital X equal to 1 is actually 4 by 16. So this is how. My question is then, my question here is now, my question is, okay, now can you tell me, can you find out the function fx, which is equal to probability of x equal to x? Can you, so from this table, okay, it is like a table. Now we have to approximate these values using a function, okay? Small of fx. So that means whenever I plug in the value of x equal to 0, 1, 2, 3, 4, I'll get the corresponding value of the probability of the event capital X equal to small x. Okay, I think you can try to find it out, but I'll give you an example. It could be written as like this: 16 and 4cx. Don't ask me how did I find it. Okay, just give it a try. So x equal to 0, 1, 2, 3, p. 4. And nobody in the world will ask you how to find this kind of a function. Okay, so this will be 0 to 1 to the. I'm just showing you an example. I'm showing that this is possible. Possible means what? I can, given starting from an experiment, I can define a sample space and I can get the corresponding value, small fx. Okay. And then I can say that this is the probability mass function corresponding to that random variable. But what I'm saying again, that you have to do two things. Either this will be given to you, small fx or some random variable, and then you have to find the properties of the random variable, or in a given data, you have to approximate this by analyzing some data. Something you have to do. You have to process that data. You have to do something. After which you have to come up with some kind of a function. Okay, so that you know that okay, so this is the probability of this event, capital X equal to small x. Okay. So this is what is the probability mass function. Then the question is, okay, the question is, I mean, now I will ask a reverse question. Reverse question means, can any function, okay, so this is my reverse question, okay. So in mathematics, what happens is whenever you define a new function, new concept, you always ask this kind of question, like, what are the properties of this small fx? Like, does it have, okay, I can see that this is a non-negative function, but is there any other property, or can any function be like a probability mass function of some random variable? That is my question now. So my question here is, can any function? So here you see this is a real valued function defined on the real numbers, because the small x can be any real number and the value is this value fx is a non-negative number. So I can say it's a real value. Non-negative means it is also a real number. So I can say it is a real valued function or non-negative function defined on the set of real numbers. So now my question is, can any function f, okay, from R to R, or can I say R to, let's say you can say 0 to infinity, whatever you want to define. Okay, can any function be a probability mass function corresponding to some random variable? That means some random variable or some discrete random variable, let's say, because I'm talking about probability mass function. I did not define how to define this distribution function for continuous random variable, because here whatever sample spaces I have considered here, they're all finite. Okay, corresponding to some discrete random variable. Why I'm asking this question? For example, suppose I have defined this one. Okay, you may also define something else. Okay, now the question is, so the question is, whenever I define this function, okay, is it uniquely defined, or I can find some other function also which has the same property? Say, there may be many functions, right? Because it is, you see, this is stable. This table is nothing but like an interpolation, okay? You can draw x-axis, you can draw y-axis, and you have 4 points, and you have to match 4 points. That's it, okay? So you can define many functions. But the question is, I define this as a probability mass function. Why? Does it have any other property, or I found it is interesting, so that's why I defined it? Or maybe you came up with a function, then the question will be, can it be called as a probability mass function? That's the question. Okay, so
Sir,
corresponding to
the
some
function has to
random,
attain a
not
maximum.
discrete sample, but discrete.
So the function should be
Can any
bounded between
function
0 to
be
1.
corresponding to some discrete random variable? And the answer is no.
Sir, your screen is not visible.
Sir has network issues. Perhaps it was showing on the top of the
Sir
screen.
has left the meeting, I guess. वकार
Yes.
सर चले गए शायद.
हाँ मालूम है. So what can we do now? He has some network issues. It was showing on the top of the tab.
क्लास क्या खत्म?
हाँ पता
Okay,
है.
can you guys hear me now? Okay.
Yes sir.
Class खत्म नहीं हुआ. Just wait. Just wait. Let me define what is that. So many issues. Okay, So can you guys now see my
Yes, sir.
screen?
Yes, sir.
Yes,
Yeah.
sir.
Yes, sir.
Yes, sir.
Yeah.
Yes, sir. Yes.
In general, okay. In general, the answer is no. Any function, it's not. I mean, any function does not represent a probability mass function of some random variable. Okay. So then the question is, what are those functions which represent random variable? In fact, there are a lot of things here. Okay. In fact, for any, so what I'm questioning, my question to, I mean, for the physics students at least, in fact, for all the students, one interesting point here is to notice whenever I have a finite sample space, that means, so for finite sample spaces, this is very interesting. For, I mean, this is how we can connect math to and probability here, for example. For finite sample spaces, okay, for a finite sample space, let's say my sample space is S, and these are the possible outcomes, x1, x2, then xn. Now question is, what am I talking about? I'm talking about f of x1, f of x2, dot f of xn. So whenever I think this is a sample space, you assume that this is the corresponding real numbers, okay, associated with the sample points. I mean, small x of some s1, let's say. Oh, okay, let me write it in a different way. Otherwise, there is a chance of confusion. So let me write it different way. So let me say, I mean, why I was writing it this way, there is a reason. So anyway, I'll tell you, let's say this, these are the possible outcomes. Okay, now whenever you write, you define this S to R, okay? So you can associate Xi with some Xi, okay? Let's say I equal to 1 to n, but this Xi need not be distinct actually, okay? So that's why I was, if you assume that it's distinct, then x1, x2, xn, this will form a set. Anyway, that does not matter. So let's say s1, s2, sn, these are the sample points. Then you associate some numbers with that. It could be anything, depending on the context. And see what I'm talking about. I'm talking about fx1, fx2. So I'm talking about a vector. In fact, I'm talking about a nonlinear vector. Okay? I can possibly write like this. This is probability of x equal to x1, probability of x equal to x2, and so on. Probability of x equal to xn. Okay, I'm talking about this. Now, if I am talking about this, see, this need not be n-dimensional. That's why there is a problem, because this xi need not be distinct. Okay, if you assume that it is all distinct, then you can say like this one. Okay, xn. So assuming that all distinct, you can say it is an n-dimensional vector. Okay, so then the question is, if it is, let's say, n-dimensional vector, so this is some vector r to the power n, and I can say it is bigger or equal to 0 because all the entries, let's say, are non-negative. Then the question is, does any vector from r to the power n or a non-negative vector from r to the power n, that an n-dimensional vector, represent a probability mass function for some random variable? That's the question I'm asking. And if this is some sample space is not finite, but it is infinite, but countable. So that means for infinite sample space, infinite but countable, okay, sample space. So let's say S is equal to like this, S1, S2, dot, dot, dot. So what is my question here? Okay, so I can define the same thing like f of x is defined from S to R, and x of Si is equal to some xi, okay, for all I is bigger or equal to 1, let's say. Then here I'm asking the same question. The by probability mass function, my question is, it is now an infinite dimensional vector starting from x equal f of x1, f of x2, and dot, dot, dot. It goes on. Okay, so this is an infinite dimensional vector. Okay, so the question is now a non-negative vector. So the question is now, does any such vector represent a probability mass function corresponding to a random variable? And the answer is no. Okay, and the logic is also very simple why it is not. Once I define this, you'll see. Then question is, what kind of function can serve as a probability distribution or a probability mass function corresponding to some random variable? Why this question is important? Because suppose from the data, suppose there is a data and we are processing the data, and you come up with a function which you are claiming that's a probability mass function, but you first have to make sure whether it satisfies the definition of probability mass function or not. Otherwise, it may need not be. I mean, if you do not verify whether it follows the definition or not, it need not represent the probability mass function of any random variable in this world. Like I said, always need to verify, and it will be clear from the definition what should be the conditions. Okay, what should be the conditions of a function? Okay, such that that function or that vector here, for example, can serve as a probability distribution corresponding to some random variable. So this is my definition. You can call it a theorem also because you can prove it, but let us introduce this as a definition. So a function f, let's say R to R, okay, can represent a distribution function, can represent okay, or maybe can represent a distribution function, distribution function corresponding to a random variable if the following conditions are satisfied. First, if this is non-negative, okay, this is from the definition. I mean, this is from the concept only because these values represent some probability, so it has to be bigger or equal to 0. Okay, for all x, okay, whatever be the domain. Okay, here I'm assuming the domain is R, but it need not be R because it can be just the values of the sample points. So there are values where this xi, okay, it need not be entire R, but let me say it R. And other thing is, this is also very, very important, which is sum of fx should be equal to 1. So overall x, y, that means sum of these entries, okay, of all this vector has to be 1. Sum of this series means which constitute of the sum of the terms of the vector, infinite dimensional vector. This has to be equal to 1. Why? Why this property has to be satisfied the second property?
Probability total sum is 1, sir.
Essentially, f of x is probability at the end of the day, so it should satisfy all the properties of the probability function.
Okay, think about it. So this is my homework. There can be, much more things can be said about this, why it should be. So you should ponder about it. So you should think about it. Okay, why?
Sir, f of
Why?
x is p of the random variable.
What is that? Yeah, fx equal to, now see, here there is no random variable. Question is the reverse question. So we define probability mass function of a random variable. Now why we are asking a converse question. We are saying that given a function, can it be a probability mass function of some random variable? We don't know what is the random variable, but can it be? Can it be considered as a candidate, okay, which can serve as a probability mass function? That is the question we are asking. Because I can,
Sir,
so this, because of next, yeah.
Sir,
yeah.
Sir, this function cannot be always increasing, no?
I did not say anything about increasing. Need not be.
Sir, because if it is increasing, then for increasing x, the value of fx would increase, and at some point it would cross the value 1.
No. See, no. See, the thing is, so that's why I gave you this one. It is a vector. Think about it as a vector. Okay. What do you mean by increasing? Yeah, that is also a question. What do you mean by increasing? So although here I said that the domain is R, actually domain, as I said, this are all those xi's. But anyway, you can think about R also. So maybe, okay, let me say, read like this way. So this is x1, let's say this is x2, okay, and dot xn. Now what I said here is fx, which is, if the random variable is given, then this can be expressed as, if capital X is the corresponding random variable, then this should be expressed as this. But that is not given to us. Okay, my question is the existence, that does there exist some random for which it is true. So this is not given to me. So if it is not given to me, I have no comment about the probability of this. So it could be here, it could be here, it could be here. What is that? Okay, it could be here, it could be here, again it could be here, it could be here. But sum of this should be equal to 1. Okay, this is, so it is not increasing, you can see. Okay, I mean, I am writing it as like x1 is less than x2, but it need not be also. So it is like x1 could be here, x2 can be here, here it could be x3, and here it could be xn. Okay, depending on the values of x size. Okay, the way you can define. But anyway, so you can assume like this is the entire real number, this is x-axis, and then there are some values, okay, for which you are calculating the probabilities. Okay, and these values you can assume like it is x3, x4 up to xn. Not a problem. Okay, so next question is, this is the I'll end up.
So the domain
Yeah.
of f of x is the all the values of random variable is equal to the values which it can take. For example, f of x ka domain would be let's say the random variable is capital A of x and x is 1, 2, 3. So a of 1, a of 2, a of 3, this set is the domain of f of x.
No. See here. And that's why it is a little confusing, but anyway, that is not a problem. See here, what did you say? When you first introduced this, I said x can be anything. This x can be anything. But if you take only these values, then only these probabilities are non-zero. Otherwise, you can take x any number, like say x equal to 100. But if you put capital X equal to 100, then that would represent the null event, okay, whose probability is 0. So these are only the non-trivial events, okay, correspond to the small x, this will have a non-zero probability. But in principle, this x can be anything because your random variable can be any function. Okay, so in principle, this small x can be anything.
Yes, sir. Understood.
Yes, wait. So the here we can take this function to be equal to x equal to r, doesn't matter. Even if you, yeah, go ahead. So another question? Yeah, please.
Sir, how our probability mass function know that this experiment or this random value is not possible?
Which random values?
So suppose that in the previous rolling dice experiment, if you put x equal to 100, then how the probability mass function know that?
No,
like if we
in that
another way, like a 4cx or a 4p.
I don't understand the question. So here, if you, okay, so in this example, the point was?
Sir, if we define a function like 5cx.
Yeah. Oh, so that one. Yeah, 4cx. Here you are saying this one.
Yes, sir.
Yeah, what is the question?
Because 4c100 is not possible, no? X has
like
to be less than or equal to 4.
Okay. So here I said, see, x equal to 0, 1, t4. So that's why I said this is like an interpolation. I am only matching with this one. But in principle, when you define like this, you can say that otherwise this is 0, x, which is r minus this. You can define as 0.
Sir?
Can you guys hear me?
Yes, sir. Sir?
Yes.
No, we can't hear you, sir.
Can you hear me now? Can you hear me now?
Yes, sir.
Okay, so
Yes,
what I was, yeah. So what I was saying, just a minute.
Sir,
I
in the
don't know.
definition of PMF, In the definition of PMF, sir, what are the other conditions? We got stuck on
Those
two
two
only.
are no, those two are the conditions. I don't need anything. Yeah, so here you are saying 4C100 is not possible. 4C100, I mean 4CX I defined. Can you see the screen?
Yes, sir.
Yes, sir.
Yeah, 4CX I defined. I said x equal to 0, 1, 2, 3, 4. I did not define it for other values. For other values, you can say fx equal to 0. Like if you take x equal to 100, you can say fx equal to 0. For other values of small x, this is probability is always 0. So I did not define it for the other values. Okay, for other small x. So this is non-zero only when it is 0, 1, 2, 3, 4. Is that okay now?
Yes, sir. Understood.
Hello. Okay. Okay. Any else? Okay. So your question is, what are these are only two conditions. These are the two conditions only. That's what you need. That's it.
Sir, so any every PMF will satisfy these two conditions, but any function which satisfies these two conditions cannot be PMF, right, sir?
Come again. Repeat again. What is the question?
Like every PMF will satisfy these two conditions, but the converse need not be true.
No, the converse is also true. If a function has these two properties, then it can always be treated. It can serve as a PMF of some random variable.
Of some, okay, some any. I mean, we don't know which, but some.
Yeah, for some random variable. Yeah. So this is the definition. When so it is my homework. Okay, if you have some other work, you can go. I will upload a slide so that you can see the question. Question is, okay, let what is going on here? Okay, so the question here is, let fx equal to let me just say that x plus 2y 25 and x equal to, let's say, just 1, 2, 3, 4, 5. Okay, let fx be this. My question here is, does this represent a PMF? That's my question. So whenever I say PMF, that means PMF corresponds to some random variable. And here you can say like these are the only, so it is a discrete random variable and so on. Yeah. Yeah, I think we'll end the class here and meet next week.
Thank you, sir.
Thank you, sir.
Yeah. Okay. Okay.